We're going to continue on with homework number 18. In this case, we're going to do unit conversions. To access the content for this, come to the APMonitor.com/CHE263, and then on the right hand side you're going to see homework. Go ahead and select that link and then scroll down to homework number 18. You can see some of the source files. Again, this is done originally in MathCAD, but we're showing you how to do the solution in Python as well. So just go ahead and follow along. The solutions are posted there for 1 through 7, and this is going to be 8 through 10. Okay, so the very first thing that we want to do is go ahead and see if pint is installed. Okay, so no module named pint. So what we'll do is, instead of before importing pint, we're going to import pip, and then with pip we'll do pip main, and then in brackets here we'll do install, and we'll do pint. Okay, so this is how we it's going to go out and get the pint package, install it, and it says successfully installed it. Okay, so if you want to come back in, if you want to share this script with somebody else, you can do try and then do import pint and then accept it. Okay, so if it doesn't work to import it, then we're going to go ahead and pip install it. I'll just put this import pip down here as well. Okay, and then we'll import pint. Okay, so it's going to try to import it. If it doesn't find it there, then it's going to install it and then import it. So pip is a way that we can manage packages in Python. Okay, and we can do that with Anaconda as well. Okay, so there I have pint installed, and then the very first thing that I want to do is just whenever using pint, I like to do a unit registry. Okay, it just kind of gives me all the units, and then I'm also going to do q equals u dot quantity. You'll see why I'm going to do this later. Okay, so this is all part of the import of pint. Okay, so let's go to our very first example. We want to convert the speed of light to miles per hour. Okay, so let's go ahead and do that. First, we're going to do the speed of light. Okay, so if I forgot about the speed of light, I can do SciPy constants as CNST, and then the speed of light is going to be CNST.c. Okay, so I'm going to do C equals and then CNST.c. Okay, if I just print C, I can see that it's going to be in meters per second, but I don't have any units there yet, so let's go ahead and add units. I'm going to do u dot meter divided by u dot seconds, and then you're going to see that that number C now has units attached to it with the pint package. Okay, and then when we want to convert it to miles per hour, we do the .2 and then mph, miles per hour, and then that converts it to miles per hour for us. Okay, you could also do miles per hour, like that, and it's going to give you the same answer. So different abbreviations, but same answer in the end. Okay, let's go up to our second problem now. Convert the density of water at room temperature from 62.4 to kilograms per meter cubed. So I'm just going to copy this in here. I'll say row density equals, okay, and then let's go ahead and do times u dot pounds. Okay, so that's going to be pound mass. Okay, divided by u dot foot cubed. And let's go ahead and print row just to make sure that's working. And then again, we're going to do 2. And then instead of the pounds per foot cubed, we want it in kilograms per meter cubed. Okay, so there it is. It converted it for us. And you can see it's just under 1,000 kilograms per meter cubed, which is what I typically use for the density of water, is about 1,000 kilograms per meter cubed. Okay, so let's go on to the ideal gas constant now. Okay, so we have the ideal gas constant, Rg, equals 0.08206. liters per atmosphere mole Kelvin, and we want to convert that. I'll just go ahead and copy this, so I don't have to type it out again. And RG equals, okay, and then I'm going to do, in this case, I'm going to do something a little bit different. I'm going to use that Q, okay, function that I created earlier. It's a quantity, and then the very first argument is going to be the number, and the second argument is going to be the units of that. Okay, I'll put a comment there, and let's see if this works. It's liters. I had to put a multiplication there, times atmospheres, divided by moles times Kelvin. Okay, and let's go ahead and print that out as well. So there's atmosphere liter per Kelvin per mole. Okay, so that looks correct. And then we want to convert it to joules per mole Kelvin. Joules per mole Kelvin. And there you have 8.31. Okay, joules per mole Kelvin. Okay, let's go ahead and do the next one. So here we have to BTU pound mole ranking. Okay, so pound mole ranking. This one's going to be just a little bit different because we have, pound mole is not defined. Okay, so you can do pound mole equals U dot LB divided by U dot gram times U dot mole. Okay, you could try to define it that way. Okay. Alright, so that'd be one way to define a pound mole, but anyway, I'm just going to go ahead and print this out. Print RG2, and then let's do BTU per pound divided by gram, okay, times mole times degree ranking. Okay, so let's see, I had an error here. Let's check out this error. I'm going to go all the way down to the error. Dimensionality error, cannot convert from one to the other that I requested. Okay, so let's go back and see what the problem is. Looks like I forgot the parentheses there. Okay, so there it is, 1.9859 BTU, and then this is going to be pound mole. Okay, so there's the next one. Let's go ahead and do convert 300 cubits to yards as well. Now in this case, cubits are not defined. Okay, U dot cubit. For example, it's going to give me an error. It couldn't find it. Okay, so in some cases you just have to make the unit conversion yourself. Yard per cubit, and it's 0.5. Okay, with the length of 300. Okay, and so in some cases you just don't have the units there for you, so I create my own unit conversion, factors, scalars, things like that. Okay, times yard per cubit. Okay, so if that happens, then you just have to do it yourself, and you can't rely on pint to do it for you. You can also modify pint, extend it to add additional units if you use those a lot. Okay, so that's the very first one, kind of an introduction to pint. We installed pint with this try except using pip if it isn't there, and it installs it. You could also do uninstall if you wanted to uninstall it. Okay, and let's go down to the next one. We have a volume of a cylinder that's going to be given by V equals pi r squared times L, but R is going to be equal to 25 times U dot feet, and the L is going to be 5 times U dot meter. Okay, and then we want to be able to create our volume, and I'll do pi times R squared. Okay, if you don't have NumPy yet, okay, if you're just starting this, you do import NumPy as MP, and then times L. Okay, let's see this one. Okay, so quantity squared. Okay, didn't like something about the r squared there. Squared. Okay, let's see, I have an r squared here, and I have v equals np.pi times r squared. Let me see if I can figure out what's going on here. And I need to get this in barrels eventually, so I am going to go ahead and put this in. Let's see, I've got something wrong. Oh, I know what it is. I just had to do the squared like that. Okay, so there I have it, foot squared times meter, so it puts it into a volume that preserves the original units, but if I want to put it into foot cubed, then there it is in feet cubed or meters cubed. Okay, now I'm going to show you what you can do if you want to put it into barrels. For example, I'll do BBL. Okay, it's 42. Different definitions of barrels, so you can't necessarily use one definition of barrel, but I'm going to use the one that's common in the oil and gas industry for like barrels of oil, which is 42 gallons per barrel. Okay, and then what I want to do is do V divided by BBL. Okay, and then you can put 2 and then put blank here, and that'll come out dimensionless. But this number will be in barrels because I've divided it by the 42 gallons, and it canceled those units out and put it into barrels. Okay, so that's one way to do it with the barrels. Let me go on to problem 10 now. I have a rate of heat transfer from a heated flat plate. So this one I might need to draw a little bit just to show what's going on with the this problem. So let me go ahead and draw this flat plate. This one's just a little bit more complicated, but it's kind of a good example of a real unit conversions problem, this one involving heat transfer. Let's go ahead and just open up, I'll open up OneNote here. Okay, so I have a flat plate here that's hot. Okay, this one's going to be hot, and you have some fluid flowing past it with a certain velocity. And what we want to do is calculate from this hot plate how much heat is lost. And that's going to be our Q value. And so there's going to be a couple different numbers that we're going to calculate, a Prandtl number, a Reynolds number, and then we'll get on to a Nusselt number, and that will give us a heat transfer coefficient, H. And then from the heat transfer coefficient, we're going to have Q per area is going to be H times delta T, or if you had an area, you'd have HA delta T. Okay, so the delta T is going to be the difference between the fluid, okay, flowing over the top, and the hot plate. Okay, so the temperature difference between those two. Okay, so let's go on to the problem now, and what we're going to do is do a rate of heat transfer from this flat plate, calculating a Nusselt number with all of this information in here. You can read through it. I'm just going to go through it pretty quickly, and then what we'll do is just go ahead and go back to the problem if you have any questions about it. The precursor information, I'm going to do a quantity and do 80 comma U dot degree C. That's going to be my temperature of my plate. And then my water flowing over it, my fluid, is going to be Q. And these are going to be different units, but it's going to take care of those for us. Okay, so degree Fahrenheit. And then the length of the plate is going to be 1 times meter. And then my delta T, this is my delta temperature, is going to be T H2O minus T plate. And then let's go ahead and just print that out. I'm going to show you, the delta T here. It's a delta degree Fahrenheit, and that's important because it's not in an absolute scale. But if I convert it to like a Kelvin, for example, then you're going to see it's going to be a delta T in Kelvin instead. Okay, and then let's go on to our velocity, 1.45 times meter per second. And I could have used the Q function to define that for me as well, but I just opted to do it this way. 0.979 times U dot centipoise. Okay, that's a unit of viscosity. And then my density, we showed density before, 62.3. And then I'm going to do pound per foot cubed. Okay, and then thermal conductivity, 0.347. That's going to be BTU per hour times foot times degree ranking. Okay, and then the heat capacity. This is all for the water. Okay, the water is, depending on how fast it flows and its properties, it's going to give us a different Reynolds number and Prandtl number that we're going to be able to use to predict a Nusselt number. So let's go on with our Prandtl number now. We're going to take the mu, the viscosity of the water, H2O, times the heat capacity divided by the thermal conductivity. And let's go ahead and print the Prandtl number. Now, one thing you'll notice here is that the the Prandtl number is going to show up with dimensions, and so it should be dimensionless. Let's go ahead and just check that. And if I cancel out those units, it's going to cancel and give me the same number, but without the units there. So those units are able to cancel. Now let's do the same thing with the Reynolds number as well. These are dimensionless numbers. H2O. Okay, the length of the plate times the velocity divided by mu H2O. And let's print Reynolds number and make it see what it is a dimensionless number. Okay, so there it is. There's a dimensionless number. All the units cancel. And Nusselt number as well is going to be dimensionless. It's just going to be a function of the Prandtl and Reynolds number. Okay, so these were kind of experimentally determined, different fluids. And so these are some correlations from heat and mass transfer. Okay, I'm just going to convert the Nusselt number permanently to be dimensionless, and then I'll print Nusselt number. Okay, and if I don't do this, then I'm going to get some really funny units there. It doesn't really cancel them out. Doesn't kind of identify that it's able to cancel those out. So I just need to do the unit list, make sure that it's dimensionless, and give me a number there. Okay, now let's go on to calculating the heat transfer coefficient, and that's just going to be the Nusselt number times K divided by the length of the plate. And let's go ahead and print this out. And this one is going to be watts per meter squared times Kelvin. Okay, if I print that out, there I have my heat transfer coefficient in the units that I'd like it. And then let's calculate my heat transfer now, and that's going to be my H times delta T. If I had an area there, I could do it instead of units of heat transfer per area, I could do it as absolute heat transfer. And so I'm going to put this into units of calories per centimeter squared per minute. Okay, so I have a heat transfer rate, and so I'm losing 38.8 calories per centimeter squared per minute from this hot plate. Okay, so just to review, we did units here. We did conversions from like the speed of light, density, ideal gas constant, measures of length. Okay, we went on to problem 9, just calculate the volume using a radius and a length that were in different units, and this converted it for us and put it into barrels eventually. And then problem 10 was a more realistic heat transfer type problem with lots of units, dimensionless numbers, a lot of information there, but we wanted the heat transfer rate in calories per centimeter squared per minute, and so we did that with these calculations here. Okay, so pint is an effective way to do unit conversions. There are other packages as well in Python, but this is definitely one of the better ones that's there.